Hello. So first, is this anyone's first The Long Con? Awesome. Excellent. Congratulations for being here. Thank you for being here. Because without you, we don't have things like this. So we love having, we love having new people and seeing old friends. So I am Mike Saunders. Today I want to talk to you about intro to AV and EDR Evasion. If you do want to copy the slides, you should be able to get them at redsiege.com/stealth. They should be available for you. And that's me. I'm Hardwater Hacker on most of the socials, and you can reach me at mike@redsiege.com if you have any questions. I am the principal consultant for Red Siege. I've been in IT for a long time, and I've been doing security full-time for the last, well, this hasn't been updated now, it's 17 years, but I've been in security for a minute. And when I'm not doing computers, I like to be as far away from them as possible. So, yes, thank you. So first, what this talk isn't. This is not an advanced evasion talk. We're not going to be talking about things like unhooking and evading runtime checks with EDR and things like obfuscating your comms. Like those are different talks. So this is an intro talk on AV and EDR evasion, like very intro. Getting your payloads onto disk, getting your payloads into memory, not unhooking, but like just getting them onto disk and to the point that you can do things with them. So you got to be able to crawl before you can walk, before you can run. We're not going to talk about like the comms side of things, but we will talk about evading common brittle detections that are in AV. We'll talk about what that looks like. And we're going to talk about this concept of entropy as well. So the first thing I want to talk about is what gets you caught. What are the simple things that get you caught? So anyone here familiar with the MS build technique? Know what MS build technique is for code execution? All right, we got one person. So the MS build technique has this common template that people use. The 3G student template is where people start a lot. And it works great. However, because it works great, companies write detections for these things, and they're brittle detections. So if you were to just use the 3G student template, it's going to get signatured by pretty much any AV on the market. And we look at it, what are some of the things? Like the task name is called class example. And there are things in the code. So the MS build technique is a way of executing code. MS build ostensibly is for building things, MS build. But we can take a specially designed XML template and actually execute code with it. And there are things in there, if you were going to load some shellcode into memory and execute it, the template has some defaults in there, like the function address, which we need, is part of that. The variable is called funcadder. And conveniently, our shellcode goes into a variable called shellcode, right? So some of these things right there are going to be detected if you didn't change it. However, because AV is brittle, just changing the name of variables is enough to get you going. So there's a start right there. Like, change these defaults when you're getting example code to start your payloads. This is still valid today. PowerShell is not dead, even though people tell you PowerShell is dead. PowerShell is still out there, and there's lots of PowerShell templates. And I have seen this not too long ago. This still happens. Comments that are in a PowerShell script, not even the functional code, just a comment. Like, you see sub-T or harmjoy or something like that in a comment, and AV's like, this is bad. Like, I don't know what the rest of this is, but I see sub-T in here, so this is obviously bad. Anyone know who Casey Smith is? Like, it's wizard. Casey is a wizard. And if sub-T shows up in your code, AV's like, we're not having any of that. I don't know what you do, but this is obviously bad. But removing the comments, simply removing the comments. So there's a blog here where the author is talking about, they were doing this test, they run this PowerShell script, and it gets detected. And they removed the comments from the PowerShell script, and it worked fine. They were literally just detecting these 3 lines of code, lines of comments. So removing comments, something that can get you caught. Not obfuscating common code execution patterns. And whether that's a script, an MS build template, compiled code, there are things in your code that are signs that you're trying to do something bad, maybe. And not obfuscating those can get you caught. So if you're using C# in something like an MS build template or in your, so especially in an MS build template, you've got this template, this code, this XML document that it can read. If you want to allocate memory using virtual alloc, and then you want to create a thread, we need to allocate memory, we need to move shellcode into memory, and then we need to create a thread to execute that shellcode. We need to use these functions, virtual alloc, create thread. I have seen AVs and EDRs throw up a detection on a template that doesn't have any functional shellcode in it. Like, it doesn't do anything, but because we called virtual alloc, or not even called it, we imported it. And this is what this statement, the DLL import means: import from this DLL this function that we're going to use later on. Simply having these 2 things in an MS build template will lead to a detection. Whether or not you use them, just DLL importing them is a way of getting caught. So we're going to talk about that in a bit, how you can get around that. There are some other things like strings that show up in your compiled executable can also get you caught. So in this case, I'm using a tool called Defender Check. There's a newer version called Threat Check. But what it does is it takes a file that you want to check to see, is this bad, and detects it, runs it against Defender. And it does what's called a binary search analysis, right? So we take a piece of code, and then we split it into 2 equal-sized pieces, and we check both of those pieces. Are either of these bad? If one of those is bad, take that bad piece, split it in half, check both of those halves, see if one of those is bad. And you keep narrowing it down until you find the exact bytes where a detection occurs. And in this case, it's this right here: module not found, error mimikatz do local. So it's seeing mimikatz, it's finding this string. So a fun way of getting around this, call it Mimi something or other. Mimi dogs, like that has worked. Simply changing cats to dogs has been enough. So take the source code, just search and replace every instance of cats, replace it with dogs, and AV was like, seems legit. This is good. So know that the strings that are in the code that you're compiling could be enough to get you caught. So sometimes you have to remove the help messages, or you have to change the help messages. You have to change the error messages. Another thing that can get you caught is entropy, but we're not ready to talk about that yet. So those are some of the common things that get you caught. So what do we do about that? Well, we need to make our malicious code look like it's not malicious. We need to blend in and just look like a regular, everyday executable or bit of data sitting on the disk. And there are some weird ways of blending in. So I had a template that worked for a long time. Like template, I mean like some example code that I would just substitute in my shell code. And it worked for the longest time against Defender. This shellcode loader just worked, no problem. One day, it didn't work. And it's getting detected. And I can't tell why it's getting detected. And like any good coder, you know, I'm throwing in printf statements everywhere, trying to figure out where I'm getting caught. And I can't even run my code. It's just like getting schwacked as soon as it's compiled. So I do the other method of debugging, which is start removing code. Which function is causing the problem? And finally, I've removed everything from my shellcode loader except the encryption routine. So right down here, you can see Zor optimized.exe is what's being detected. Zor. That is the key. It was my encryption routine. I'm using Zor encryption. And by just having this Zor encryption, I wasn't doing a single byte. I was doing like a multi-byte Zor. So if I had a single byte Zor, excuse me, that obviously gets detected because that's really easy for AV and EDR to brute force that Zor and be like, now I see your shellcode. So we use a multi-byte key, which makes it much harder for them to brute force it. However, apparently in the real world, people don't use Zor with multi-byte keys because by doing that, that is a sign that you're trying to hide something. So Defender was like, I have no idea what you're doing, but this is bad. And no matter, so I tried, like, I know it's Zor. So I tried all these different types of ways of compiling it and throwing in extra steps in my Zor routine to try to change the signature of my code. And no matter what I do, remember back here, it's saying, you know, offset, found at this offset. It's telling you exactly where in the code the detection's occurring. Well, the detection is occurring in the exact same spot every time, no matter what I do. So has anyone ever heard of compiler optimization? Okay, so a few of you know what compiler optimization is. You compile something, and the compiler looks at it and goes, I am smarter than you, and you're a bad programmer, and you did not make this very optimized. So I'm going to try to optimize this for you. So I'm trying every possible solution to fix this, and my coworker says, well, what about compiler optimization? I was like, that can't possibly be it. Like, take a look at the file name. Zor not optimized, no threat found. I literally compiled it and disabled compiler optimization. So the compiler did not try to make mine more optimized. Now it just said, I'm going to take whatever you have, and that's fine. By simply turning off compiler optimization, my payload worked. So now when I compile payloads, I disable compiler optimization because turns out like they just distill that down into the essence of the code and then, hey, that's bad no matter what you do. So disable compiler optimization, one way to get around detections. Very stupid, like this, things that shouldn't work. Actually, if you have a chance, my coworker Corey did a talk this year. I think it was called That Shouldn't Have Worked. And it's just like, you know, stupid human tricks for getting code execution. So I would encourage you to take a look at that as well. So another thing that you can do to get around detection is renaming entry points. So we talked about in the MS build template, I had to do a DLL import, right? So we're going to take out what this looks like. Here's a couple of good references for learning about entry points and declaring those and how they work. But this is essentially how we declare a function in C#. We're going to DLL import from kernel32.dll, and we're going to import virtual alloc. We want to use virtual alloc. We need to be able to allocate memory, so we need virtual alloc. This form right here is detectable and does get detected. However, there are ways of getting around that. So if you read up on DLL imports, if we were doing this in C, like you could actually encrypt the name of the function that you're importing, and basically that gets you around detection a lot of the time. But as far as I'm aware, it's not possible to do that in C#. However, there are things we can do. So here, this is the exact same thing as this slide. Exact same thing, does the exact same thing. But I say for this entry point, virtual alloc, there's some other options that you can set, like set last error and exact spelling, and you can change these up. And fun fact, if set last error occurs after exact spelling, that's a different signature, right? right? That you've changed it. It's a different signature. So sometimes just reordering things can be enough. This is Splendid Dragon. What is Splendid Dragon? Anyone know what Splendid Dragon is? It's virtual alloc. Like a random word name generator that I have came up with the word pair Splendid Dragon. So now when I want to allocate memory in my code, because I've declared this as entry point equals virtual alloc, but I'm going to call it Splendid Dragon. So when I want to allocate memory in my shellcode loader, I call Splendid Dragon instead of virtual alloc. And Defender and some EDRs look at that and go like, all right, it's not virtual alloc, it must be okay. This works. Like, why would that work? It's stupid. But that's what when I said brittle detections, that's what I mean. They're very brittle. There's like, I'm looking for this exact order of bytes. I'm looking for this exact order of words. And by simply changing that order, the fingerprint is different. It's a different signature, and they're looking for exactly that signature. And that's kind of the difference between AV and EDR to a point, right? Like EDR is looking at behavior, AV is looking more at just signatures. However, a lot of EDR has an AV component that you also have to get around, and this is how you get around the AV component of it. So now we know some things that get us caught. We know some things to get around getting caught. But we still have the problem of our payload, our shellcode that might be a Cobalt Strike Beacon, might be a Metasploit interpreter payload, it might be Nighthawk, it might, whatever it is that we want to run. We need to make that look like something that's not malicious. And that presents a whole lot of problems. So, let you think about that for a second. How do we do that? We need to make it look like it's something it's not. We need to make it look like it blends in. So, how do we obfuscate shellcode? A fun one that came about a few years ago, NCC group did some research into the Lazarus group. And there were a couple of cool things about this research. One was how they were executing shellcode. They were using this routine called enum system locale A. So basically figuring out like what is the language of this system. For some reason, that call has the ability to execute shellcode. Amazing. Why should it do that? Don't know, but it does. But the other really interesting thing that came out of that research was how the attackers were storing the shellcode. So have you heard of a UUID or a GUID? Like, you know what that is? Yes. So universally unique identifier, globally unique identifier. It is a way of structuring, it is a specifically structured piece of data that's supposed to uniquely identify something that is in this impossibly large key space. So like instead of ID equals 1, we give them a UUID and we don't have to worry about key space collision ever. Everyone's going to have their own unique identifier. So what Lazarus Group did was they took the shellcode and they stored it as UUIDs. This is shellcode. This isn't a bunch of UUIDs. So this is shellcode. It's shellcode bytes, but because we structure it and it looks like a UUID, AV and EDR was like, seems legit. No problem at all. Like, I have done this with zero encryption. Just take shellcode, break it into however many characters that is in each string, and put some dashes in the right places. And it's like, oh, it's a UUID. This is fine. We don't have to worry about it. So this is shellcode right here. Like, you can structure code as UUIDs, and I've done this recently, and it works. I've got shellcode loaders that use UUIDs to store the data, and it works a lot. So there's some other ways that you can do it. You could take your shellcode string and just reverse it, like put it in reverse byte order, And then right before you use it, reverse that string in memory and then execute it. That works. You can break it into chunks, and it does work. However, it's really tedious because there are going to be certain bytes in shellcode that define how the shellcode works. So like, because shellcode is a program, and programs have headers that occur in specific places. And so there's going to be little bits of fingerprints in those bytes, and breaking it into chunks is really tedious, trying to figure out exactly where you need to break it up. Like you can, and then you've got 1,000 different little A equals, B equals, C equals, and then you concatenate those all back together right before you use them. You can do that, but it's tedious. Another way that my coworker Justin came up with, which was kind of fun, break your shellcode into an array of even and odd bytes. And I don't mean by value. I mean by their position in the array. So because we start with 0 for numbering things, the zeroth array, a position in the array, the first position, but it's value 0, that is an even. So put that in one array. Take the second byte of shellcode, put that in your odd array. Put your third byte of shellcode, which is even, into the even array. You go back and forth, and you now have 2 arrays of your shellcode. Good luck detecting that. Like, that's going to be very hard. And then right before you use it, you iterate through those arrays and reconstruct your shellcode into one big piece. And this works. Like, we have used this technique, and it works against a lot of things. There's also steganography. Like, steganography is this idea of changing the least significant bit of color or alpha value in an image. And by changing that bit, you can encode data into an image without significantly degrading the quality of the image, especially if you do it in the alpha channel. And that's something that we see a lot with like some ransomware actors doing. Their loader goes out and grabs an image. That doesn't normally look suspicious. Things go out and load images from the web all the time. And you can have this image that has data stored in it that doesn't significantly increase the size of the image. And there's no real way to detect that looking at that image unless you know what the key is. So we could use stego. Another thing that we can do is just use a different language. So Go, for instance. Go works great. There's not, if you build something in C, or if you build something in C# or C++, those are languages that have been around a long time. There's a lot of instrumentation built into operating systems that allow them to look into what's happening in that code and understand it. Use something like Go or Nim or Rust, and they're like, I have no idea what this is. It's a program, seems legit. Rust, I question whether Rust is actually going to continue to be viable like that, considering Rust is going into the Windows kernel. I have a feeling that there's going to be a lot of visibility instrumented into that code. But just taking a loader, earlier this year I spent a bunch of time developing loaders, a bunch of different loaders, and I was writing them in Rust, taking no steps to do obfuscation, just writing a shellcode loader in Rust. And Windows was like, Defender was like, seems legit. This is okay. The same exact thing written in C, it was like, no, get out of here. Only difference was I wrote it in a different language. So we can write our code in different languages. So I said we talk about entropy, and we're going to talk about entropy. And I do want to say, I am not a mathematician, so this may not be exactly correct. I'm talking about entropy as it relates to information theory, not the heat death of the universe, although those things are related, but I'm talking about information theory. I'm also going to talk about this idea of Kolmogorov complexity. So it's easier for me to show you than to tell you this stuff. So, entropy is the measure, again, Don't throw things at me because I get this wrong, but it's essentially a measure of the amount of randomness in something. So if something is very high in entropy, we can say it is very random. If something is not very random, it's very low in entropy. Why are we talking about entropy? So one of the most common ways that we hide our shellcode is we encrypt it. But the act of encrypting our shellcode makes it very random, which means the entropy is really high. So if you look at something, you see the entropy is really high. Without knowing anything about it, you may be able to infer that something is being hidden because the entropy is really high. Why do we know that? So let's take a look at that. But before we do that, I want to take a little diversion. Let's say you're not using compiled code. Maybe you're using a PowerShell script. So I talked about changing variable names, right? So the first thing you might think about is like, I will write a parser that will take this PowerShell script and it will obfuscate all the function and variable names. And the easiest way to do that, let's just take each value and generate some random characters for the name of that function or the name of that value. I would discourage you from doing that because even in a short amount of data, a few characters, there's entropy there. And I have been caught by an EDR or an AV, I don't remember which one, but basically looked at my function names and variables and they were randomly generated character strings. And it said, I have no idea what this is, but just by the fact that all these functions and variables are random, you're trying to hide something. So therefore, it's bad. So the way I get around that is to generate random words, and rather random word pairs. The reason I don't use just a random word is because there is the chance, depending on the language that you're using and the dictionary that you're pulling your random words from, that a word you choose is a reserved word in the language that you're developing in. Now it's broken because all of a sudden it's like, hey, you're trying to give me a command, but that's already a command I already know about. So, but if we generate random word pairs, the chance that you're going to run into a collision is, I'm not going to say it's zero, but I'm going to say it's very low. So always generate random word pairs. If you're doing anything that's client-facing, make sure your dictionary is sanitized because it would be really uncomfortable if you were to use the Google top 10,000 word dictionary as your data source, and then, like, statistically it shouldn't work out. But the number of times that I've generated something with the dictionary and be like, whoa, I cannot give that to a client, like with that combination of words. So make sure you spend a lot of time sanitizing your dictionary. All right, back to entropy. So I said we're talking about high entropy and low entropy and how we can tell that something might be bad. Well, we know that languages are not random, and I'm talking about languages that we communicate in, English, German, Spanish, whatever. There are lots of tools for measuring entropy, but we can use gzip as a good proxy for measuring entropy. If we gzip something and we use the verbose flag, it'll tell us how much it compressed something. So I just took dictionary.txt, an English dictionary. I compressed it. I was able to compress it by 64.7%. Now we know because of Kolmogorov complexity that the more random something is, the less compressible it is. The more random it is, the less compressible it is. Vice versa, the less random it is, the more we can compress it. We compressed this by 64.7%. So we don't know what the actual measure of entropy is, but we know it can't be too high because we compressed it quite a bit. Did the same thing with the German dictionary. I compressed it by 75.9%. So we know that German is more terrifying than English and less random. So, side note, if you want to learn about like how to use languages to hide shellcode in a really cool way, like basically putting like a Shakespeare sonnet in your payload, and that's actually your shellcode, like you can do that Some really smart people did that. Read these documents. It's smarter than I am. They're way smarter than I am. So go read that, because I'm not going to talk about that. But why am I talking about entropy? Anything that I am sharing with you is the result of something that I have experienced on a test. Like, I've ran into this in the real world. So last year, I was testing CrowdStrike, and I get this payload, and I drop my payload on disk, and the difference between like traditional AV and like an EDR, AV is probably going to scan that as soon as it hits disk. EDR is going to scan it when you go to use it. I drop my payload on disk, I try to run it. Nothing happens, like nothing happens at all. So like any good developer, in come the printf statements. A bunch of printf statements. First thing, like program starts to load, print, hey, I'm starting up. Nothing happens. I was like, well, this is odd. Like, it's not even printing that. So it's not getting killed once the program's running. It's not even allowing the program to run. What about my program? So it's making a decision that my program is untrustworthy for execution, but without ever executing it. So what is it doing? Like, what can it know about my program before it starts to run it? After talking to some smart people, like all of us kind of agreed it might be entropy. So it's a really stupid solution, and yet it works. Take a bunch of non-random data. What is non-random data? Like, what's the source of non-random data that we could put for something? A book, the web, words. I took a bunch of words and I compiled a gigantic character array. I didn't use it. Again, turn off compiler optimization, because if you have a variable that you don't use, the compiler's like, I don't know why you put that in there, I'm going to remove it. But if you disable compiler optimization, it's like, cool. So now I have this variable, this character array full of thousands of words. We know that languages are not random. They're low in entropy. I have shellcode that's high in entropy. If I have an executable that contains both of these, the very low entropy data that I just compiled in lowers the overall entropy of the executable. And CrowdStrike was like, cool, and lets it run. And this was me. Like, that can't possibly have worked. And yet, it worked. And this is literally what it looked like. Like, if you looked at my code, there's a character array that's just a bunch of words compiled into the program. And that was enough. Now, obviously, the way I loaded the shellcode, the way I executed the shellcode, and the things that I did once the shellcode was running, all of that had to be okay as well. And that's like an advanced talk. That's EDR evasion. But this was what we had to do to get it running in the first place. Like, that was the first step. Simply doing this, like, it's not great. It took a long time to compile. You need a lot of memory. The compiler's like, I have no idea what you're doing, but you're dumb and I don't want to let you do this. And yet it works. But guess what? There's a simpler way. You could take this non-random data. Anyone familiar with cat? The program cat? Cat program dictionary.txt redirect to new program.exe. That will concatenate your binary program and your non-random English words and append those words to the end of the executable. Or you could do cat dictionary redirect to the end of the executable. And that will actually work. Like, it's the amazing thing. We didn't mess with the program header, and Windows does not care about what happens with the end of the program. It's just like, whatever. It's there. I don't know what to do with it. Cat a picture of a cat onto the end of your executable. That will actually work, but I believe it's got to be a PNG, because JPEG data is binary. I think it's got to be a PNG. Don't quote me on that, but you can literally cat a picture onto the end of a program, and it will lower the entropy. So let's take a look at this. The first one is my original Cobalt Strike shellcode loader, and it contains AES encrypted shellcode. I can only compress it by 18.4%. Now it's small, right? Like it's a very small program. It's 362K. But I could only compress it by 18.4%. Kolmogorov complexity tells me that I can't compress this very much, so the entropy must be very high. And we know that because we just gzipped it and we couldn't compress it very much. So I take the same thing, the same program with the words compiled in. The only thing that's changed is the words compiled in. I compress it by 97.8%. Super compressed it, which means the entropy in this must be very low. That was the only difference between these two programs, is a bunch of English words added to the executable, and Cobalt Strike was just like, I got nothing. So this works great. Another side diversion, not related to entropy, but fun with words. Back in 2018, some researchers were testing Cylance. Fun fact, your favorite EDR vendor probably has their corporate new AI, ML, whatever buzzword engine. If they also sell a home product, they're the same engine, just not without all the management tools. So they were testing Cylance's home product, but it's essentially the same thing as the corporate product. And they started reverse engineering this executable to try to understand what it's doing and how can they get around the AV. They ended up figuring out that there's this huge dictionary of words in there. Like, where did this dictionary of words came from? Well, apparently, what they found is there was a really popular game in 2018. I don't know, maybe Fortnite or something. I don't know. But anyways, whatever that really super popular game that everyone wanted to play, there was something about it that Cylance was like, this is bad. Well, that's bad for Cylance's business. If people can't run the games that they want to run, they're going to get a lot of complaints about that. So they literally took all of the strings that occurred in that game and added them into their engine that said, if these strings occur in anything you're looking at, it's okay. So these researchers then figured that out. They took like the top 500 malware samples off of like VX Underground or something. I don't know. Like they ran 500 different kinds of malware through Cylance, and like 98% of them, Cylance was like, cool, you're good, by simply putting these words in there. So if you want to research how to get around the next gen AV, a home license probably doesn't cost you very much, and that's something you could play with. So another stupid human trick that we can do with shellcode and programs is just make them really big. Why, you might ask? Well, it is expensive to scan things that are big. And in the business world, if things take too long, people complain. We have performance impact. So your little program doesn't take very long to scan. But if your program is 500 megs, that takes a little bit longer to scan. And depending on the engine, some of these will do it by default. Some of these are configurable for the size. Some of these don't care what the size is. But if you have one that does make a decision based on the size, if you make it larger than whatever that threshold is, the engine just says, too big, not going to scan it. So you can just pad your executable with data, whatever that data is. You could pad it with random data. You could pad it with zeros, and both those work. However, because of the entropy problem, you might not want to do random data. So there is a program that Matt Eidelberg he used to be with Optiv, he's with Black Hills now. What is that program called? Is it Scarecrow that does it? I don't think it's Scarecrow. He's got a program that can be used to inflate executables, but it padded it with random data. So pad it with a bunch of random data. We've introduced entropy into something that's already high in entropy because their shellcode's encoded, are encrypted. So I created DigDug, does exactly the same thing. Anyone Does anyone get the Dig Dug reference? Please tell me. Yes, thank you, thank you, thank you. So Dig Dug game, those of you who don't know, back in the 80s, this guy ran around with this air pump and then he would blow up bad guys, inflate them. So Dig Dug just takes a program and pads it with words from a dictionary of your choice. And if it gets big enough, things won't take a look at it. I promise you I am not targeting CrowdStrike. It's just the thing that I come up against the most, and it absolutely works even today against CrowdStrike. It's now about 500 megs, but if you have a 500 meg executable, back in the day, we were all about making our loaders as small as possible because we had to get them in through really, slow internet connections. But now everyone has fiber everywhere and it's super fast. 500 megs is nothing. Shellcode loader that's 500 megs is just good. And blowing it up gets you past detection. So there's something you can take a look at. But let's talk a little bit more about evasion. So jargon is like special words or expressions that are used by particular people. So like all of the various acronyms that Richard just talked about in his last talk, that would be examples of jargon. It means a lot to people who know SSO, and to people who know nothing, like IDP what, OIDC what, I don't know, that's jargon. So what is jargon? What if we could take shellcode and make it words so that instead of having shellcode in our loader, we just had words, no shellcode at all? We would solve multiple problems. One, we don't have raw shellcode. And because we have words, we haven't increased entropy because we know that languages aren't random. How would that work? It's stupidly simple. And I do want to say that I did not create this technique. I'm just the first person to release a tool that does it and talk about it publicly, as far as I know. There are some books where someone talked about this, and someone told me it once, and I can't remember which one it is. But let's say the shellcode byte 00. We need to store that. We could store it as an int, as a 0. Fun fact, we could also store it as a 00. And we could store it as a bunch of other ways. But let's say we could store it as a 0. How many different possible shellcode bytes are there? 256 possible values. So if we wanted to use words, all we would need to have is a dictionary that has at least 256 unique words, and each word could represent a byte of shellcode. What does that look like? We need to create a translation table. And so you see, it's a translation table, contains 256 entries, a bunch of words. Doesn't matter what the words are, as long as all the words are unique. Source words could be anything. What if the source words came from kernel32.dll? That would make an analyst scratch their head looking at your payload and what are all these function calls? What is this? I don't know what it is. Doesn't matter, bunch of unique words. We create a translation table. In each position in the table, its position represents the byte. So if it is in the first position, in position 0, it represents a 00. If it is in the last position, it represents an FF, and so on and so forth. And so what we do is we look at our shellcode, we look at the value, and then we do a lookup in our translation table, see what the word that matches at that position, and then put that word into a new array that's storing our shellcode. And so this is what it would look like. This happens to be a Cobalt Strike Beacon. Bunch of words just showing up all over the place. And then when we want to use it, just some dirty, simple C. In this example, we have 2 loops. One loop that loops through every byte of the shellcode, and then for each byte of the shellcode, let's take a look at a translation table and see what position it's in, and then put that value, position 0, into an array. Now we've stored a byte of 00 for shellcode. When we do this, we end up with an executable that's going to be bigger than if we just added that data onto the end of the program, catted those words onto the end of the program. but we've got no shellcode in our shellcode loader. And again, very compressible versus just straight encrypted shellcode. Does it work? This is a program. It's translating my shellcode. Boom, Cobalt Strike beacon. So it works. You can absolutely use this. It works against a lot of EDRs. I don't know of any that it doesn't work against, and we use this in our loaders quite a bit. If you want to try it, I would encourage you to check it out. It's actually at Red Siege's GitHub now, but this will redirect to you. So if you go to GitHub Hardwater Hacker, that's me, or GitHub Red Siege/Jargon, you can download Jargon and check it out for yourself. A few other closing thoughts. Could you store shellcode as emoji? Yep, you can. Someone did a talk, not this year, but last year at DEF CON. They did it for the RISC-V or RISC-V architecture, but you could absolutely store emojis and represent shellcode. The world's unlimited. Cobalt Strike Arsenal Kit, completely unrelated, but if you use Cobalt Strike and you're not using the Arsenal Kit to modify your payloads, you're doing it wrong. You absolutely need to be doing that. Lastly, check out the Sector 7 Institute courses. These are great courses for getting into learning techniques for writing tools that'll get past AV and EDR. They're like $250 US a pop. I'm not paid by them. I just think that they're great courses. Definitely check it out. If you want the slides, you can get them at redsiege.com/stealth. I've got the links to the tools here. We have a Discord that is the official Cobalt Strike support Discord. You can go check that out, redsiege.com/Discord. Every Wednesday, we have something called the Wednesday Offensive. It takes place at 12:30 to 1 p.m. Central Time on Wednesdays. We have interesting people who are doing interesting things in the offensive and defensive security spaces. Come on and tell us about cool stuff they're working on, hacker war stories, all that kind of stuff. You can find that redsiege.com/Wednesday Offensive or WEDOFF. This is me. Feel free to follow me on Twitter, X, all that stuff, and follow Red Siege to find out new tools and blogs that we have coming out and webcasts and that kind of stuff. So with that, thank you for being here, and it's question time. Questions? Thank you. Thank you. Or find me outside. But any questions? Yeah, the question over here. Yep.
Well, you demonstrated a lot of very easily understood techniques. Are you seeing these out in the wild?
Yeah. So the question was, I demonstrated a lot of like easily understandable techniques. Are we seeing these in the wild? Some of these techniques came from things I've seen threat actors use, and these are things that I use in all my shellcode loaders in one form or another. These are baked into the loaders that I have. So yeah, absolutely, they're being used, and I know through talking to peers in the industry that they're using same things. That shellcode as words, Jargon, Ballast Kit, the Shellcode Pack Pro, they actually incorporated that technique into building their payloads. Yes?
I'm not super well versed with C#. The obfuscation that you showed us by changing the entry point to the DLL, that's pretty much just like offsetting your literal entry point, like offsetting your DLL. It tries to find that function name, it fails, and it just goes offset 0x00 in its mind. Goes to that.
You talking about where I renamed the entry point?
Yeah.
So the question was how did that rename the entry point work, and was it something with an offset? And it's not even that complex. You're literally just saying, when I want to use virtual alloc, I'm going to call it Splendid Dragon, and that's it. And then in your shellcode, you just say Splendid Dragon. There's no offset. You're just saying, I'm remapping this word to be this word, and that's enough for it to be like, oh, okay, cool. Yes.
So when we're using DLLs, aren't those things actually strings in the DLL that we could rename?
The question, when you're using DLLs, aren't those things in the DLL? I don't know about being able to rename like in the DLLs. Like you can do it with the entry point, renaming the entry point. And in C, there's a way of doing it basically using like get proc address. And so you get a pointer to that function, but call it whatever you want. You can do that. But I don't know about actually being able to rename the DLL because you don't control that. Like you'd have to be able to write to that memory space, and the DLL is probably,
Oh, yeah, so you're linking it runtime, not
yeah. Any other, yes, in the back. Yeah, so the question is the entropy threshold, and did I do that by trial and error? Actually, there was like no trial and error. Like I came up with that solution and it worked, and it was like, all right, move on. I haven't done the testing to figure out where that entropy threshold is. There just hasn't been a need. Like I know that I can lower it and it works, but there is definitely some threshold, but I don't know what it is. And I've been told, at least with shellcode pack, that like that particular technique using shellcode as words is sometimes being signatured, but I think it's something in the way they're implementing it because we aren't having that same problem. So, any other questions? All right, well, thank you everyone, and thanks, Longcon.